Hello friends, I'm back with a video on OPAMP as inverting amplifier. Now, before we move on to understand how this works, we'll have to get the basics, the basic theory of operational amplifier as inverting amplifier. The operational amplifier is a differential amplifier which basically amplifies the difference between the two inputs, that is V2 minus V1 at the output. So it can be used as a non-inverting amplifier, inverting amplifier and differential amplifier. What we are going to do is we are going to now see how the operational amplifier can be used as a simple inverting amplifier. In our case, we will be considering IC 741, which is a 8-pin single OPAMP. Now, how do we identify the pins of the operational amplifier? It is an 8-pin dual inline package type, hence there will be 4 pins here and there will be 4 pins on the upper side. Now it is a plastic package type, and on the plastic package type you will see a notch being built on one side of the operational amplifier IC. Take it on the left hand side and then start counting anti-clockwise. That means if I consider the notch to be on my left hand side, I will start counting the pin like 1, 2, 3, 4, 5, 6, 7 and 8. In a very similar fashion, I have the IC with me. You can see it is a 4-pin on this side, it is having 4 pin on this side, and it is having 4 pins on this side, and this is also having a notch here. If I bring it a little closer, you'll be able to see it. Yes, the notch is here. The notch is here, also a dot. So count from this: 1, 2, 3, 4. This is 5, 6, 7 and 8. Okay. Now if we have a look at the input of it, the second terminal is the inverting terminal, third terminal is the non-inverting terminal, sixth one is connected to the output. This is negative supply, and this is the positive supply. Now we are having two pins. Number one is for offset null correction, and number 5 is again for offset null correction. This is minus VEE. It accepts a maximum of minus 15 volts, and this is positive VCC. It accepts a maximum of 15 volts. Okay, so pin number 1 offset null, pin number 2 inverting terminal, pin number 3 non-inverting terminal, for negative supply, five again offset null, 6 is the output pin, 7 is the positive supply, maximum is 15 volts, here is minus 15 volts, number 8 is not used in case of IC 741. There are only few ways of identifying which pin acts as what. Now, whenever you try to identify the pin numbers, there are three techniques. The first technique is you look for the notch, take the notch on the left hand side, start counting from the bottom anti-clockwise. Similarly, look for a dot. If you see the dot will be usually closer to the pin number 1, then again start anti-clockwise. Now suppose there is no notch, no dot. How to find out? Look for the name or the number on the IC, take it straight, count from the bottom left side anti-clockwise. Okay, now let's have an idea about OPAMP as an inverting amplifier. Now, to do that, we will take the operational amplifier, take the input resistance, calling it R1, take another resistance, we will call that the feedback resistance from the output as RF, Since we are using the operational amplifier as inverting amplifier, we will disable the inverting pin. The non-inverting pin. We will apply a voltage at the input of R1 and we will get a voltage at the output V0. Now let's try to analyze what will be the relation between output voltage, input voltage, R1 and RF. Now let us label this as Vg and apply Kirchhoff's current law at the input, or we can do it in another way, apply KVL at the input, that is Kirchhoff's voltage law. Now whenever we apply any voltage at the input, it is actually applied between the ground or the circuitry ground and other input. So we can write V1 is equal to I1 R1 plus Vg. Now we can write this as I1 equal to V1 minus Vg by R1. Okay. Now we all know that the operational amplifier is having an infinite input impedance. From the ideal characteristics of an OPAMP, we understand that the input impedance is infinite. So if the input impedance is infinite, we will not expect any current to enter into the operational amplifier. Rather, the current which is available here will flow through RF. So what we can write is in the second section, what we can write is Vg is equal to I1 RF plus V0, that is the output voltage. Now rearranging the terms, we can write I1 is equal to Vg minus V0 by RF. We could have taken this current as IF, but since no current enters into this section, the entire current is expected to flow in this direction, and hence we can call IF is equal to I1. Now, when there is no current flowing into this device, we will not expect any voltage drop across this. Hence, this Vg will be at zero potential, and this is called a virtual ground. Virtual ground can be seen only in inverting amplifiers. Now, why do we call it virtual ground? Since it is not exactly connected to the ground directly, but still its potential is zero, and hence we call it virtual ground. Now, if we consider Vg to 0, what we get here is I1 is equal to V1 by R1. Similarly, what we get here is I1 is equal to minus V0 by RF. we also know that I1 of this expression and I1 of this expression is same. Equating these two, we get V1 by R1 is equal to minus V0 by RF. Rearranging the terms for V0, what we get is minus RF by R1 into V1. Now, if RF is equal to R1, we can write V0 is equal to minus V1. Now, what we can see is, under this condition, if V1 is given a voltage, say 1, what we get is a minus 1 at the output. Now, this minus 1 means that the signal is 180 degree out of phase. The expression is of a lot of importance to us. Here we will arrange the term again. You can see this, and we will call this closed loop gain V0 by V1 equal to minus RF by R1. Closed loop gain, we can see that here the output voltage can very well be controlled by just having different values of RF and R1. We can provide a different sets of gain by just adjusting RF and R1. It was not the same in the previous case. In the previous case, what we had was an amplifier OPAMP having V1, V2 output V0 with a gain of AOL. We could have written that as AOL V2 minus V1. We have already discussed on the ideal characteristics that this AOL is infinite, but in practical case it's very large. And since it is very large, a very small change in V2 minus V1 will actually give a very large value of V0, which is again restricted to the maximum supply voltage of the operational amplifier. If the difference is positive, the output may reach near to plus 12, and if the difference is negative, the output may reach near minus 12. We will call that saturation voltage. So it was very difficult for us to handle the output of the operational amplifier when there was no loop. What we used here is a simple feedback resistance which actually provided it a negative feedback, and we were able to control the amplification of the operational amplifier. Now, we will just have a look at the operational amplifier using 741, use some values of RF and R1, provide an input and see how it behaves. But before we move on to the practical part of this, we would need to understand a few more things. Well, before we move on to the practical side of it, the operational amplifier will be connected with an RF with the input resistance R1. We will be grounding the non-inverting terminal, that is the third terminal. Second terminal will be connected with the feedback. We will be having a plus 12, minus 12 volts, and we will provide a variable source at the input so that we can change the input and measure the corresponding output. Now, before we move on into this, what we will do is we will take few sets. Let's consider set number 1, where RF is equal to R1. Now, this can be done if you choose RF equal to 10 kilo ohms. Now, we will always prefer to choose the resistors in kilo ohms range. Now, if RF is 20, if RF is 10k, definitely R1 will be 10k. What we will get is a gain of 1. Now, then we will take set number 2, where RF will be twice of R1. Similarly, set number 3, where RF will be thrice of R1. Now, when we apply the set 1, that is RF equal to R1, here the relation would become like this. So, if we plot it on a graph, this is plus V1 plus V out minus V out minus V out, and if I provide a positive input, I will get a negative output. That means if I provide a positive input, which is here, I will get a negative output. So, let's take an example. Suppose Vin is 2, suppose V1, V out, Vin is 2, we will get minus 2. Suppose it's 3, we'll get minus 3. It's 4, we'll get minus 4. And if it's minus 2, we'll get plus 2. If it's minus 3, we'll get plus 3. If it's minus 4, we'll get plus 4. And we can then start plotting them in this. So, what do we get? We get a positive value V1 and negative value of VO. So, if it is 1, 2, 3, 4, minus 1, minus 2, minus 3, and so on. Similarly, minus 1, minus 2, minus 3, minus 4. Similarly, 1, 2, 3, 4. The first reading that we are getting is input is 2, output is minus 2, hence here again input is 1, sorry, input is 3, it's minus 3. Similarly 4, minus 4, and again this, and so on. So what happens, what we can see is we get a straight line. We'll get a straight line which is actually passing through 0, because if we provide a 0 at the input, we'll get a 0 at the output. So we can see that the characteristics actually pass through 0, and it is between this quadrant and this quadrant. It is between this quadrant and this quadrant, and it is bisecting this at the angle of 45. Okay, now whenever we do this, we'll have to make sure that there is no error at the output. Now error may occur if there is an output offset. It may happen if there are some internal problems to it. Now, to do that, we need to go for an offset null adjustment. We will take up the offset null adjustment and the other necessary circuits in our next video, where we will demonstrate how to construct a inverting amplifier using operational amplifier. Thank you very much for watching this. Stay tuned for the next video.